Hey, welcome back. And it's actually now when the fun really begins. I know that many of you are pretty stressed now with Project One. And I didn't expect to see so many fails here today. And the guys, you've been doing heroic jobs with the projects. Thanks a lot. And we really look forward to read them and grade them and give you feedback. Now, the topic today is actually us getting into deep learning. And that is going to keep us busy for most of the rest of the semester, which means that we will, after neural networks, we are going to cover convolutional neural networks, which is actually the method when it comes to image recognition. We are going to look at recurrent neural networks, which is the kind of method of choice if you want to analyze time series, but it's also the entry points for large language models. And then depending a little bit on how the semester evolves, we may look at autoencoders, which is another deep learning method, and perhaps also say something about unsupervised learning. But and perhaps include also decision trees and random forests and so on. But if people are more interested in, let's say, deep learning, we will just stay with deep learning for the rest of the semester. So the topic now today is to step you through how you write your own code for neural network. And that's essentially the topic of project number 2. Now, project number 2 is something which we will present next week, but the exercises this week is the first step of setting up a neural network code. And we have some simple exercises which we hope can guide you through that. So a neural network consists of 2 steps. One is called a feed-forward step, and the other one is called the back-propagation step. So the feed-forward is actually you grinding through the whole network and producing an output. When you have produced the output, you calculate the derivative of the cost function, the gradients, and then you propagate backwards. And that's the back-propagation algorithm. And essentially, backpropagation is you applying the chain rule of derivatives. So the complication now comes via the fact that you don't only have a derivative of the cost function, but you also have a derivative of the cost function with respect to all the parameters previously to the output layer. Okay? And that's the backpropagation algorithm. The backpropagation algorithm gives you the gradients. It's a recipe via the chain rule to get the gradients. Then, when you have the gradients, you apply gradient descent. So this is where you are going to reuse what you did in project 1, but now applied to a series of derivatives. I'm trying to go through the basic steps through some simple examples, and then next week, that's when I will go through how you build your own network, but also the exercises this week and next week will contain this week feed-forward, and next week the back-propagation part. So hopefully then we will get you all started with writing your own code for neural network. And then the kind of data we are going to look at are both classification problems and the standard regression problem which we had in project 1. So you're going to write a more flexible code, which allows you to attack different data sets, either continuous one or discrete ones. Now, what I have here, if you now look into the material this week, I hope I didn't overwhelm you with all these videos, but actually so some of them are pretty good. So if you have time and you don't have anything else to do, take a look at these videos. Some of them are pretty good. And there is also the video on backpropagation, the video on neural networks, building your own code from scratch. So these are all elements which we will go through. Now, the textbook by Rashka, the one which we have been using, actually in chapter 11, it has a very good description of how you write your own code. And in chapter 12, it uses PyTorch, if you want to use that. So we are going to scratch the surface in 2 weeks on how to use TensorFlow and PyTorch to set up your own neural network code. But essentially what you are going to do now in project 2 is to write your own code. And this is something which is doable typically in the span of 3-4 weeks, which is the time we have for project number 2. If you look into the exercises this week, there are some basic elements here of a neural network. And we are going to set up the feed-forward part, essentially, of a neural network code. And then the week after, we are going to plug in the back propagation. So following the steps which you see here, you should then be able to have your own code for a neural network. And again, the weekly exercises are exercises which you can recycle directly into the project, as before. Okay, any questions so far? Another thing I wanted to point out to you before we move on, if you are interested, the mathematics of deep learning. So deep learning is a field where you could say it has been packed with, let's try and see what happens. And then it works, but we don't understand fully why it works. And in the last decade, I mean, the field of mathematics of deep learning is a field which has emerged. And there's a lot of interesting mathematics and a lot of things to explore. And if you're interested in that, this is also something which you can suggest for project number 3. So every year, we had people who wanted to study specific properties of neural networks in project 3. So those of you who are more mathematically inclined, you could then explore different mathematical approximations. That's a viable variant of project number 3. So these 2 books, if you're interested in looking at them, they give you a kind of a starting point for the mathematics of deep learning, which, as I said, is an emerging field. Often in science, you have experimentation and trial and error. Like when quantum mechanics was developed, the whole theory of Hilbert spaces was something which was lacking. And then in the 30s and 40s in the last century, this was a field which developed itself mathematically. Then we have Rashka's book, which I, again, would like to recommend strongly now, because it has a lot of code examples, especially for neural networks. And it also contains PyTorch examples, if you want to use PyTorch as a library and programming environment. So how many of you have actually used PyTorch? Let me see if somebody has used it. Okay, 1. And we are going to look at both TensorFlow and PyTorch and how to use them to set up a neural network code. So these are efficient libraries which, in a way, do in a more compact way what you are going to do in project 2. But project 2, you're going to reuse your gradient descent algorithms from project 1 and write your own neural network code. That's the basic aim of project number 2. And it's going to be available next Monday. The reason for that is that I guess you're pretty fed up now, project 1. So the idea of getting started with project 2 this week is probably not the most exciting one. So we will just let you guys just breathe a little bit, and then we begin again. Okay. So let's, so the lab session, as I said, is just the exercises, is just to set up the feed-forward part of a neural network. So this is essentially what we will be dealing with this week. Now, what I want to do now, just quickly, so this is something which we discussed last week. And I wanted to, so if you scroll down, this is just a quick repetition. We are going to look at what's called also a multi-layer perceptron. So we discussed the single perceptron model last week when we studied logistic regression. Actually, and this is something which is fun, when you have your own neural network code, when you take away all the hidden layers, you can actually do a classification problem, which is equivalent to you having a logistic regression code. Because a logistic regression code or setup, as we said last time, is a recipe where you feed in the input variables from your design matrix. These are weighted by some parameters which are unknown, these weights. These are fed into a function, which is this one. So we have all the inputs coming in, and these are fed into some function, and then you spit out a value. This value, y, which is your model, is then compared to some output target through the cost function. And it's the cost function which is the quantity you optimize, as we did with ordinary least squares, lasso ridge, etc. Okay? Now, a neural network is extending this one. So this is typically called a simple perceptron, and this is inspired from neuroscience. So you could think of this as a neuron which gets a signal, and then it sends out a modulated signal. It could be a threshold here, which simply says that if the value is below a certain value, then it outputs 0 or it outputs 1. So this is a typical case when you're looking at a binary classification problem. Now, when you have a neural network, you're actually going to feed into different hidden layers, and you will have many more parameters which you need to train. So in the case which you have here, the parameters to train are these weights here, as we call them. Whereas here, you are going to have a series of weights plus so-called biases, which we're going to introduce in just a few moments. So the more layers, yeah? No, the cost function is that it receives your output. So in the figure here, if you look at, so this is actually a little bit important. This is your model now. That spits out an output, which then goes into the cost function. So the output is what is compared with your target values. Now, your neural network is going to have parameters for every layer, but you're going to produce a final output, which then is compared with the target value. Then you have to go back. So you start with these values given by random numbers. You initialize it randomly, and then you send your input through the whole network. The network then produces an output. That is the feed-forward pass, first step. Then, since all the variables were initialized randomly, you may get something which is just crap. Then you compare that with the target values in the cost function, like the mean squared error. Then you take the gradient of that. But then what you need is also to train all these other parameters. And that's the back propagation, where you set up the chain rule and find all the derivatives. And all the derivatives are then trained by the gradient descent method. And we are going to see that example by example today. So this is a more generic picture here. So I'm going to skip some of these and then come back to the technicalities for the full network. So we're going to go through some simpler cases first. But I wanted to remind you of some of the basics here. So we have an architecture here. That is our model. So let me just increase the fonts a little bit. So the network contains an input and output layer where you define the inputs X, and then you have an output, which is your model, which is then compared with a target value, as before. Then you have a given number of hidden layers and units, or nodes, as we call them, or neurons. This can vary. This is the complexity of your model. And then you have activation functions which modulate the input to every layer and produces an output. And this function here becomes a variable of your model. A typical function which has been used, which was very much inspired, again, by neuroscience, is this sigmoid function, or the logistic function, as we called it last week as well. Then, when you have this, you have the final layer, which is the output, And that has an activation function which may be different. So you can have, let's say, 100 hidden nodes in the second last layer, but then the output layer is perhaps just sending out 1 or 0. So there will be only one output. So the activation function of the output layer may not be the same as that of all the hidden layers. It's common to have the same activation function for all the hidden layers, because else it's easy to just get lost and don't see the wood for trees because you have too many parameters. But the output layer is tailored to the output. So if you want a function value, it's normal then to just spit out what the last layer gives without any modulation. But if you're doing a classification problem, if you have a multi-class problem, then this activation function is often the softmax function, which we discussed last week. Or if you have a binary case, it's just a logistic function. Yes, no, 1, 0, etc. And then we have the optimization problem. So the cost function is then a function of the unknown parameters. And then we need to calculate the gradients of that function. And the typical parameters of a network are the so-called weights and biases, which we will define in more detail today. Then you have other ingredients. And this is where everything else, which you did in project 1, comes into play. So you have various Newton methods, you have a gradient descent, you can have a gradient descent with momentum, adaptive gradient, etc., and stochastic gradient descent. So everything you did in project 1 were in a certain way using gradient descent on lasso, not on ridge, and ordinarily squares is actually an overkill because you have a nice analytical expression you can just invert. So, but here you will need it. So this ingredient is a very important ingredient of a neural network. And then we have other parameters, which could be the hyperparameters you have in lasso and ridge. And it's pretty common to actually include them as well and play around with different hyperparameters, as we will see next week when we are going to build our own code during the lecture. Okay, any questions so far? Now, there's something I wanted to state here. And I'm going to use the slides before we go back to the whiteboard. So there's something which is called the universal approximation theorem, which is a central theorem in neural networks. So before that, people would play around with neural networks. It could train decently, but you didn't understand properly why it gave these results, which it gave. Now in 89, Sibenko and then later Hornig, they actually showed that any continuous sigmoidal function, like the one we've been discussing, given a continuous deterministic function f of x, this function f here, which is a function which is unknown, and a parameter eta here, larger than 0, then there is a one-layer neural network, which is this one, with parameters theta, where you have the weights and the biases, which we will discuss in more detail. And these are represented by matrices and vectors, where the difference here can actually be driven to a small error. So you can approximate any continuous function with a neural network with at least one hidden layer. Now, the theorem doesn't say how many nodes you need. It doesn't say what the size of the error is. That is left to experiment. And that's why you have to think of a neural network as a numerical experiment. Now, there are many parallels, and what you have encountered in project 1 is a variant of the Stone-Weierstrass theorem for polynomial approximations. You could also look at the convergence criterions if you're familiar with that for Fourier series. And there are lots of these kind of theorems from real analysis where you can show that the expansions converge with a given error. Now, the thing is that you don't know how big this error is, but it guarantees that there is a convergence. if some specific properties are obeyed. So we are not going into the proof. So what you can say then is that, and this was actually extended later by Hornig, so any continuous function supported on the unit cube in d dimensions can be approximated by a one-layer sigmoidal network to arbitrary accuracy. And what Hornig did was actually to extend the theorem by letting any non-constant bounded activation function to be included, using that the expectation value of the function is smaller than infinity, and then you can actually show that this expectation value is smaller than a quantity epsilon here. And that's the generalization of the theorem. So none of these proofs give you any insight on the relation between the number of hidden layers and nodes and the approximation error, nor the magnitudes of the unknown parameters. So it cannot tell you a priori. The only thing it says is that you can approximate a continuous function to a given error, but it doesn't tell you what the error is. That is the same as you would have if you were to use the Stone-Weierstrass theorem. You can approximate a function with a polynomial to a given error, period. Okay? So it means that there is a solution there, waiting just for you. Okay? And then one of the things which you would then see is typically that the theorem is applied to continuous function. If f of x is discontinuous, it won't in general be possible to approximate it. However, you can find an approximation even if it fails in certain points. So the universal approximation theorem is the theorem which saved the day and made neural networks very popular. So this was in the end of the 80s and the beginning of the 90s of the last millennium. And then neural network really took off, but there was a problem with the training. And one of the problems with the training, when you use a sigmoid function, which is very flat at the ends, and you will see that soon, is that the sigmoid function could become zero or flat. When it's flat, the gradient is getting close to zero. And this was a problem of vanishing gradients in the training of a neural network. This was roughly resolved by one of the authors of the textbook by Goodfellow, Benjo, and Courville. So Benjo got the, I think he got the Neumann Prize in computational science. And they resolved the problem in 2010. And since 2010, this has become a kind of date for when we usually say the start of the deep learning revolution. And then we got convolutional neural networks simultaneously a little bit before, recurrent neural networks and much more. And then it just took off. And you know the results nowadays with ChatGPT, for instance. Okay? So what I'm going to do now is to go back to the whiteboard, and we are going to look at the way we are going to train a neural network first in a very simple way, because I want to link this training with the way we calculate the derivatives, the back propagation algorithm. And when we calculate derivatives, we have this algorithm which is called automatic differentiation, which we are going to discuss in more detail next week. We are going to mention it today. But let's now try to look at a simple case so we get a little bit familiar with a neural network. Okay, so let's switch now. So this is you will find much of the same here, but we are going to look at a much simpler case. So let's do that and switch to the whiteboard. So we are going to look at a case which is simpler than the exercises this week. So in the exercises this week, we are going to have a vector first as an input. Now we're going to have a scalar. And we are going to look at first an example without a hidden layer. Just that you get acquainted with the way we calculate these expressions with the chain rule, okay? And the chain rule is important because that is at the heart of automatic differentiation. You will also see that there is another very important aspect. When we are setting up many of the functions, we want them to be given by simple mathematical functions, exponentials, tan hyperbolicus, etc., whose derivatives are easy to set up and also easy to implement with automatic differentiation. So let's now look at a very simple case. So this is our warm-up exercise. So this is the warm-up. And this is a case with all scalars. No vectors, no matrices, whatever. And this is what we would call a one perceptron model, or simple perceptron model, which means no hidden layers. And we are going to use this graphical way of representing things. So what we're going to have now is an input x. X is a scalar, just a number. Then this is going to be weighted with a parameter W1, which is an unknown parameter which we want to train. This is now fed into an activation function. And this activation function, we are going to call it sigma 1. We don't need to define it now, but it has an argument, C1. It also receives an input here, which we call a bias. So it doesn't have anything to do with the bias variance trade-off, but it is used in case W1 is by accident 0, because if W1 is 0, nothing happens. So this B1 is normally set to a small random value so that the training can start. If you by accident initialize your random parameters, it could happen that one of them is 0. So this is actually done in order to avoid that. Then this produces an output, and now I'm going to use the names which I will use throughout the derivation of the algorithms for a neural network. So the output here is now called A1. So this is the output. So this is a simple perceptron model. There's no hidden layer. Now, this is then fed into the cost function. So the boxes are in my drawings here. They are the cost functions. And this receives y. This is the target value. So we are going now to have a cost function c, which is a function of this a1 of y and the parameters theta, where theta now is a collective container for w1 and b1. Okay? This is essentially the same way we are going to set up the code for a neural network. So you're going to define a cost function which receives an input from your model. So what you have here, these steps here, this is your model. So let's just ring this out. So I'm going to put these dots here like this. So this is our model. So a neural network, the architecture of the network is your model. As you, in project 1, you defined a polynomial, which was your model. Okay, so let's continue. And we are going to make life a little bit easy here. So we define this sigma 1, which now gets an input with z1. And this z1 is simply given by x times w1 plus b1. So w1 and b1 are the parameters. Then you could have as an example, sigma 1 of z could just be 1. This is the standard sigmoid function of e of minus z. So z is just the argument. Now, the thing which is particular with this function, which you see immediately if you plot it, so sigma 1 of z here, so we have 0, and then we can put 1 here, is that this behaves something like this. So this is my best attempt at plotting this function. My drawing skills are pretty bad. Anyway, what you notice now is that when z becomes large, then this function sigma 1 of z goes to 0. No, sorry, not to 0, it goes to a constant. That was not correct. So when it goes to a constant, when you take the derivative, this is going to be a flat function, and then you will get derivatives which are getting close to 0. And that has created, for many, many years, a problem in the training of a neural network. So I'm just anticipating something which is going to come here. So when we now are going to continue with this example, so this is something I'm going to put in here. So preparing for later and automatic differentiation. So preparing for later means in this case, 1, automatic differentiation, but also the back propagation algorithm. So what we are going to need is the following. We need DC, dW1, and we want to have that one to 0, and DC, these are the two parameters we have. And then we need to optimize the cost function. So here we could set up a very simple cost function. So we could now decide that the cost function is just going to be the standard mean square error. So in our case, here, we could now say that C as a function of A1, the value we want to reproduce, Y, and the parameters theta is given by 1/2. And then I have A1 minus Y squared. In this case, we have only one data point. I put a factor of 1/2 because when I take the derivative, I get rid of the factor 2 from the derivative. So this is a kind of a standard which has been introduced in the literature. So what we also need now is to remind ourselves that this A1, the output, is simply given by this sigma 1 times Z1. So if you look back, we have defined the output, A1, here, as given by this function sigma 1, which now takes this as input, and where C1 is simply given by this simple model here, a linear dependence in terms of W1 and B1. And now to calculate the derivatives, we need the chain rule. And when you see the chain rule, then we also have the basic elements for back propagation, and we're also going to get the basic elements for automatic differentiation. So automatic differentiation is not you setting up a symbolic expression using Mathematica or SymPy, nor is it you approximating the derivative, but it is actually calculating derivatives to numerical precision using the chain rule with elementary functions. We are coming back to that. And this is the thing which will give you a lot of flexibility when you write your code. Because the only thing you need to do is to set up the cost functions and the activation function. And with automatic differentiation, you simply call the gradients of the cost function and derivatives of activation functions without having to hard code the derivatives and gradients like you did now in project 1. Okay, so let's continue a little bit with these elements. So what we need now is an element of the chain rule. So if we now look at the DC with respect to W1, if I now use the chain rule, so this is just an application of the chain rule, and I hope you don't get offended if I actually go through these things. So it's a DA1, it's a DA1 with DC1, and a DC1 with respect to DW1. So keep in mind that C was given by 1/2 of A1 minus Y squared. This Z1 is the one which now depends on the parameters W. So this is given by X times W1 plus B1. And then we have that A1 is actually given by this function sigma 1 times C1. So if I want the derivative of this quantity here with respect to W1, this is the quantity I want to drive to 0. You see now that I have first to take the derivative of A1 with respect to C1. Now C1 doesn't enter immediately in the expression for A1, but indirectly through this expression. So that means I need this term as well. Does that sound reasonable? So a neural network, the reason why I'm going through this in a more kind of pedantic way is simply to have you see how we are going to set up the backpropagation algorithm. And this becomes clear when we are going to introduce in the next example, one hidden layer. Then you will see it immediately, how you apply the chain rule and propagate backward. So if you now look at the expressions here, if I compute the different terms, I have a DC, DA1. That is nothing now in this simple example than A1 minus Y. So that's the derivative of this quantity with respect to DA1. Then I know that this quantity which I have, this quantity here, so let's just single that one out. This one is nothing but D sigma 1 with respect to DC1. Just keep in mind now that A1 is just given by this expression. So I'm going to label this one as sigma 1 prime. So that's a derivative of sigma 1 with respect to C1. Now, the next thing we should see, if we now take the final term, and now we go back to this expression here, you see that the derivative of that one with respect to W1 is simply X. So this kind of pattern is something which you are going to see being repeated again and again and again when we are setting up more complicated expressions. Okay? Any questions? So another thing which you will see then, when we connect, when we bring all these terms together, so let's just bring everything together. So we are going to have that DC dW1 is going to be equal to A1 minus Y. And this is the same as DC dA1. Then I have sigma 1 prime, which is the same as dA1 of DC1. That should be that one. And then finally, it's multiplied with X. And this term was nothing but DC1 of dW1. Now, what is common now is that we collect this one into one parameter, which I'm going to call delta 1. So that means that DC dW1 is actually equal to delta 1 multiplied with X. So now we have this gradient, and we need another one, which is DC of dB1. So let's go back and see what that one is going to look like. That is actually much simpler. The reason for why that is simpler, if we now spool back, is it okay if I go back? So if you now look at the expressions which we had here, I could now put B1 here. Then I would need to have B1 here. This term is the one we call delta 1. But you see now, if I take the derivative of this quantity with respect to B1, this is just 1. So it means that what I get then is simply delta 1. And now I have everything needed to train the model. So I could actually have done this for logistic regression if you wanted to. You would have to change the cost function into this binary cross entropy. If you have a multi-class, you would have to have simply the so-called multi-class cross entropy function, which we are going to discuss next week in more detail. So what we need next is the following: gradient descent. And that is the final part of the algorithm. So what we need then is an update, W1, where we have minus and then dc of dW1. And then we have B1, which is now being updated by B1 minus eta of dc of dB1. And we have these derivatives now. Okay? Any questions so far? So what I'm going to do now before we take a break is actually to do the case with one hidden layer, but still scalars. So what changes when you now have more input variables and more parameters, or nodes as we call them, is that you have to deal with vectors and matrices. Now, in this case, we had all scalars. Let's stay with scalars before the break and see what happens now when we change the model. So what we are going to do now is to improve this and have a hidden layer, but still scalars. All the variables are all scalars. So what we're going to have now is, again, an input layer. This feeds into, and then I'm going to put them in a more compact way here. So I'm going to have a sigma 1, and then I have plus this B1. This produces an output, which I'm going to call A2. This has a parameter W1. This is my first now hidden layer. So this is my hidden layer. This, sorry, not A2. I wanted, so this is going to be an A1 here. Sorry for that. This feeds in to the next layer, and this is the output layer. And this has a function sigma 2 here. It receives a new parameter, B2. It produces the output, A2 here, which then is fed into the cost function, which I just write like C here. So I'm putting arrows like that. And here we have the final Y value. So now I have an output layer which produces A2 as the output of my model. But then some magic happens inside here, where we have some more flexibility to actually adjust parameters and bring in non-linearities. So what I'm going to do now is to stay with a simple model. So I'm going to say that C1 is actually omega 1 times X plus B1. And A1 then is equal to sigma 1 of Z1. And Z2 here is going to be pretty simple, as like the previous case. Actually, this is not X here, but it now contains the input, which is A1. So A1 feeds into the next layer, and then we have A2 is equal to sigma 2 times Z2 here. Okay. So these are the models which I'm setting up. I haven't specified the sigmas. This could be the sigmoid, it could be other functions, but I'm assuming now that there is some kind of linear behavior. But what you see now is that due to this aspect here, this becomes a nonlinear function. So A2 becomes a nonlinear function in terms of the parameters W1, W2, B1, and B2. So you get a nonlinearity here, already there. So depending on the function here, you will bring in some nonlinearity. But here definitely, since you have sigma 2, which receives C2, which then contains A1, which is given by this quantity, which is then determined by this one, we have a clear nonlinear dependence on the parameters we want to optimize. So this nonlinearity is also the one which gives the magic behind a neural network, that you can fit nonlinear functions. Okay? So what we are going to do now is also to define a cost function. So I'm going to define C. Again, we are going to stay with a standard mean squared error minus y squared. So what I'm going to get then, and let's now set this up as the last one before we take a break. I'm going to get W2 here, which is going to be given by DC, DA2, and then DA2 of DC2, and then DC2 here of DW2 here. This is the same as A2 minus Y. This is the same as sigma 2 derivative, and this one is just going to be A1. So this is given by A2 minus Y multiplied with sigma 2 derivative multiplied with Y1. And now we're going to label this one as a delta 2 parameter. And it's pretty straightforward to see that DC of dB2 is actually equal to delta 2. Now we have these two derivatives, but we don't have expressions for W1 and B1. So we need a derivative of the cost function with respect to those parameters as well. And that is going to be a multiple use of the chain rule. So as I said, a neural network is you reapplying the chain rule again and again to find the gradient. And that algorithm is called the backpropagation algorithm. Okay, we take a small break. I hope you don't get offended if you see just these applications of the chain rule here, okay? But the pattern you see here is something which we are going to put to a more general neural network. And you will see that what you see here now in the simple case is what is going to be the case for the general neural network. Okay, let's take a small break. So what we did before the break was to look at a problem where we have one hidden layer. And in this lecture, we're actually going to derive the general backpropagation algorithm. But I wanted to exemplify that with a simpler case where we only have scalars as inputs. So what we found here are the derivatives for the output layer. So what we have now is the derivative with respect to W2 and to B2 here. So we have two pretty compact expressions, which we then can plug in the update of the gradients and the parameters. So that means that what I can do now is to find my gradient update, gradient descent update, of W2 and B2. Let me correct that one here. And B2, which are the output layers parameter. Output layer parameters. So what I have then is that W2 gets updated with a learning rate minus eta, and then the gradient, which is now given by this parameter delta 2 times A1. Then the parameter B2 gets updated by B2 minus eta times this parameter delta 2, where we found that this delta 2 is simply A2 minus y multiplied with the derivative of the cost function. So clearly having a cost function which can be evaluated quickly, and also a cost function or an activation function which can be evaluated easily, becomes important for the efficiency of a neural network. And this is why these activation functions, when they become parameters, because they are parameters in a neural network, why we want to have simple expressions for them, because then the derivatives are also simple, hopefully, and easy to evaluate with very few floating point operations. But what we need now are the derivatives of the two next parameters, because we need to find W1, and we want that one to be 0, and we want a DC of dB1 equal to 0. So this is the next set of parameters which we need, and it shouldn't come as a surprise that when we are finding these derivatives, we need to use a chain rule. So let's now go back to the graph which we made. So if we look back at the graph, then we had a simple expression. So if we go back here, we found the derivatives of this cost function with respect to the parameters W2 and B2. But now we need to go back to here and in here. So what we're going to set up now is just a repeated application of the chain rule. And this leads us to the back propagation algorithm, because we started here, and now we go back here to the output layer and find the derivatives here, and then we step back again, and then we have the derivatives here. So essentially what you're going to see now is a simple implementation of the back propagation algorithm. Okay? So let's just set up the final derivatives. And then when we now have these parameters, we know that DC, dW1, and this is just a repeated use of the chain rule. So we are going to have a DC of dA2. This is where we started. We have a dA2 with respect to DC2. We have a DC2 with respect to dA1, because C2 here, just to remind you of that one, is actually a function of A1 plus W2 plus B2. C1 is given by W1 times X plus B1. So I'm just reusing the chain rule here, and then I have a dA1, a dC1, and finally I have a dC1 of the W1. So what we are doing now, we are propagating back to the hidden layer by the chain rule. And essentially back propagation is us just applying the chain rule again and again and again. So clearly it becomes more and more complicated the deeper the network gets. But some of these parameters can then be easily calculated, because keep in mind now that this is something which we had before. This is this parameter delta 2. This one, if we now look at the expression DC2 with respect to A1, this is nothing but W1 there. So we take that derivative. Now, this parameter which you see here, the next one, is nothing, this one is nothing but the derivative of the activation function in the hidden layer. And then we have the final one, DC1 with respect to W1, and that shouldn't come as a surprise. This is actually given by X. Now, when we are going to set up the general algorithm for backpropagation with a given number of hidden layers, we are going to bring together many of these constants, and you will see now that this constant is a constant which I'm going to call delta 1. So this is going to be given by delta 1 times X. Now, if I then look at the DC of dB1, that is going to be given by the same expression, delta 1, but then it's going to have DC1 with respect to dB1. And if I look at the expression which I have here, you see that this derivative is equal to 1. So this is simply given by delta 1. Then I have an update rule for the hidden layer by the chain rule. So let's just wait a little bit so everybody have time to write it down. But you see essentially what we are doing here. We are going back, propagating back. And there's one reason for why we normally start at the endpoint. The main reason for that is that in a neural network, the number of input variables can be many. If you think of the design matrix, you can have thousands of input variables, but your output could be either yes, no, just one output or function value. So that means that the dimensionality of the output is normally much smaller than the dimensionality of the input, which means that when you propagate back, you start with the smaller matrices and vectors. But the backpropagation is actually us starting with a function which we want to calculate the derivative of, which is this guy here. This is the one we want to optimize. In the output layer, we have parameters W2 and B2. But clearly, we also have further parameters, like in this case, W1 and B1. So when we have these expressions, what we have now is the updates for the hidden layer. And the updates for the hidden layer are then given by a W1, which is now being updated with the previous value minus delta eta, the learning rate, times this parameter delta 1 multiplied with X. And then I have my B1, which is then being updated minus eta, and then just delta 1. So when we are setting up the general expression, you will see something similar like this again and again, where X in a given layer is given by the input from the previous layer. So since in this case, the input is just the input variable X, then in the first hidden layer, we are just going to have X multiplied with a function delta. And now what we're going to do, after just a small demonstration, we are going to show what these deltas are going to look like. And then we're going to set up the expressions for the backpropagation algorithm, which we need to code when we set up our program. So you see the basics? So essentially, backpropagation here is us applying the chain rule. We find the gradients. When you have the gradients, you update the unknown parameters by gradient descent. So the backpropagation itself is a way to get the expression for the gradients using the chain rule. So you start with a cost function where you're comparing the output of your code with the target values. So you feed everything through the network, you get an output. Then you propagate back. And in every such iteration, which contains with a feed forward step and a backpropagation step, you get new gradients. And you see now that during this training, if the gradients vanish, the training stops. Because the quantity you are monitoring are not these individual gradients. It's the cost function. So the cost function, if that is the mean squared error, you know that ideally that should be equal to 0. If it's your accuracy, you want to have a perfect accuracy, 100%. That's the quantity you're monitoring. So one feed forward step and one back going step is one iteration. And for every iteration, you update the parameters by gradient descent in each layer. And then you go back and forth. So after some 1,000 iterations, maybe your mean squared error is 0, which is the ideal. But just keep this in mind that if the gradients vanish during the training, then the training stops. And this was for many, many years one of the problems with training of neural networks, which in a way hindered the explosion of deep learning methods before we actually hit the last decade. Okay? Any questions so far? So let me just show you a quick example before we are going to set up the final expression for backpropagation. So in the lecture notes this week, you will actually find this same case. So let me just bring it up here. So if you look into the Jupyter notebook here, and by the way, I'm going to skip a little bit the discussion on automatic differentiation, which I have in the notes here, till next week. But what I wanted to show you is that essentially the example which we went through is the one which you see here. So in this particular code here, you will recognize all the variables here are the same ones which you will find in the code, in this code example. So here, I'm setting up a forward propagation. And now you could specialize this to matrices and vectors. Now, in the simple case we had, they're just scalars, okay? But what I'm doing now is to define C1, A1, and C2 and A2 as matrices and vectors. And that's why you see this math model here. But you could narrow this down to just scalars, okay? Because then it's just a vector of length 1, if it's a vector. So I'm setting up the variables, and this is my feed forward part. So in the beginning, I will initialize. So you see also I have a sigmoid function here. A1 is a sigmoid of C1, and A2 is a sigmoid of C2 here. Actually, in this particular case, I'm just performing a regression case. So keep in mind now that when you do regression, the output is just a value. So in a regression case, your output layer does typically not have an activation function. It just spits out the final value. And that should be the value of the function. But then you can have many different activation functions for the different hidden layers. But just keep that in mind. If this was a classification problem, a binary case, it could have been just a sigmoid. If it's a multi-class case, it could have been the softmax activation function. So in this particular case, you see now that I want to do a classical regression case, and then I'm just spitting out that one. Now here, I'm now setting up those parameters. So I have this delta 2, which is just A2 minus Y1, and then I multiply that one with this parameter A1. So this is essentially the parameter which we put up, delta 2 and delta 1. I have the output weight gradient and the output bias gradients. This is my hidden weights gradient and my hidden bias gradient. So this function here returns the gradients by setting up the expressions which you saw on the whiteboard. Then you can see now that what I'm setting up is a very simple case. I have an array, which is just a one-dimensional one. And then my target value is 2 times x plus 1, which in this case is just 9. I have a hidden number of features 1, number of hidden neurons 1, and output equal to 1. I initialize my weights randomly. And here I just put the bias to 0.01, just to make sure that in case my weights are by accident set to 0, I have a finite number, so the training can start. I have a learning rate. So this function, the back propagation, which I call it here, sets up the gradients. And you can see here, it returns the gradients of the weights, the bias, hidden weights, and hidden bias. So this is my output layer, which you see here named output, and then the hidden one. And my training is here. And you see I put up my learning rate, eta equals 0.1. In this specific case, I have only scalars, but you could easily change this to vectors and matrices. And this is the topic of these exercises this week, where you're going to do the feed-forward part. So that means that this week, you're going to play around essentially with this part here. So I made it a little more general because I have matrices and vectors, but I'm running with scalars here. And in this particular case, I'm just producing, this is my cost function. This is the first iteration. The second one, third, etc. You see in the beginning, the cost function is large. So I'm not writing out the gradients, but I'm writing out the cost function because that's my measure, my mean squared error. So in the beginning, it's pretty large because I have a crappy value. But then you see now that as soon as I move on, you would see that this is getting smaller and smaller. So if you can live with this as a cost function, 10 to the minus 8, which is the mean squared error, if you're happy with that one, we would stop here. So this is essentially a kind of simplified neural network code. What it essentially is doing with one hidden layer. Then clearly you can add more and more hidden layers. And this is essentially what project 2 is about. And the complexity of the model is then defined by the number of hidden layers. Okay? So what I wanted to spend the remaining 25 minutes on is to set up the backpropagation algorithm for the general case. And when we have that, that means that you, in principle, with the examples we have this week in the exercises and next week, you should be able to have the basic ingredients for designing your own neural network code. Next week, what we're also going to do is to go through the setup of a neural network code so that you have all the elements which are needed for project number 2. Okay? So let me switch back to the whiteboard, and then we are going to derive the final backpropagation algorithm. So when we now look at a neural network, a general network is going to be something like this. So we have an input layer here. So we have the input. And we have a given number of nodes here. So we would have an x1, x2, down to some xn. That's the number of input nodes. So if this is an image, every node could then represent a pixel of an image. So if you have 200 times 200 pixels, you need 40,000 input nodes to store the information about that image. Okay? So the next thing is obviously that this feeds in to the first hidden layer. And I'm going to use a naming here. So I'm going to use a hidden layer 1. And this hidden layer has a given number of nodes. So this will be hidden 1. And then we have hidden 2, now 1 here. And this goes all the way down to hidden first layer. And then we have an N1. The number of nodes, they can differ from layer to layer. The output here feeds into the next one. And I'm just going to write this in a generic way. So I just call this for H2. And this goes on. And then we have a given layer here, which I'm just going to call H of L. These are the nodes which you have. And this continues to the final layer. So this is my output. So all these are hidden ones. So we can put dots here. And then I have the output layer. And the output layer is a layer which I'm going to label with an uppercase letter L. So this produces an output which we are going to call A of L. So previously we called it A1 or A2. This goes in to the cost function, which we call C, and that receives also an argument, the target value is Y. So what we are going to look at now are just some definitions first on how we are going to set up the various variables which we will be using. So if we now look at one specific element here, so suppose now that we take one hidden layer. So we take now layer. So this is the layer with H of L minus 1. So here we would have a set of nodes, which will be H of L minus 1. This is the first one, H2 of L minus 1. And this goes all the way down to N of L minus 1. And this is layer L minus 1. And this feeds into the layer L. So we have H of L here, 1. And there's a 1 here, which we're going to call H of J of L. And that goes all the way down here. So this is H of L. Now, all these nodes here, all of them feed into all the nodes in the next layer. So this is the typical structure of a neural network. And the variables which you get, so it means that here, if we call this for I, there is going to be an output which we're going to call for AI of L minus 1. And that connects here with a weight which is Wi of J of L. So this becomes a parameter which we need to fix. Now, each such node has also its own bias. So there's going to be in here a Bj of L. So the H's are just the nodes which we have in each layer. Now they receive an input from the previous layer, which is the output from the previous layer. So that means that in here, I'm going to have a set J of L, which is now going to be given as a sum over all the nodes which we have in the previous layer. And we have an omega I of J of L, my L. I'm writing this as an L here. Multiplied with AI from L minus 1. This is the previous output, plus a Bj of L. So this is my weighted input to the activation function in that specific node of layer L. So if you think back to what we did in the simpler case, this was this C1 or C2, which then entered the activation function. So every such node, and this is pretty common, has typically the same activation functions. So that means that what this is going to produce now is an output. So let's just put that up. Output from node Hj of L, this is going to be Aj of L, and that's going to be given by the activation function. And I'm just going to use the same activation function throughout. And this is going to take the Cj of L as input. Okay? And we discussed a little bit previously that the typical activation function could be this, logistic function. So we can write these quantities in a more compact way. So I could actually write Z of L as a vector, and that would be given by a matrix. This object here is a matrix now, transposed times a vector A of L minus 1 plus a vector B of L. So this is more to prepare you guys to think in terms of vectors and matrices when you're going to set up your final code, because the weights are then given by matrices. So if you have 100 input nodes and 100 new nodes in the next layer, that matrix W will be a matrix of dimensionality 100 times 100. You will then have 10,000 parameters to tune for that specific interface between layer L minus 1 and layer L. If you continue like that, if you have, let's say, 10 layers, 10 hidden layers, then for each one of them, there will be a matrix of the same dimensionality if you have, let's say, 100 nodes in each of them. So that means that if you have 10 layers, which is a deep network, so the reason why this is called deep learning is that you can make your networks with more and more hidden layers, you can make them deeper and deeper. So the name deep learning comes simply from the number of parameters you're trying to fit. So the deeper, which means simply more hidden layers. So if you have 10 hidden layers, you will have 10 weight matrices. And if each one of them is dimensionality 100 times 100, you will have 100,000 parameters to train. So that gives you a little bit of dimensionality compared to what you did in project 1, where you indeed were looking at what we normally call baby cases with tens of parameters at most. I'm not meant to denigrate what you've been doing in project 1, because you guys have been struggling. But from an optimization point of view, linear regression is a baby case. Okay. So what we are going to do now is to set up an algorithm for finding these parameters. So let me also remind you that this A of L minus 1, this is the output from the previous layer. So that has Z of I of L minus 1. Okay, so let's start with the last layer. So we start with output layer. With the output, which is layer, which we are going to label with an uppercase letter L. So the cost function which we are going to deal with, C of theta, all the unknown parameters, is now simply going to be given by a half. And then I'm going to sum over all the variables in the last layers, the number of nodes I have. And then we have a y of I tilde minus y of I. So if we use the standard MSE, so we are restricting ourselves to a regression problem, what we have then is that this quantity is going to be this AI for layer L. So we are replacing that with that one. Now, what we want is obviously to have delta C, delta theta in the final layer equal to 0. So we want to drive them to 0. We are going to optimize the cost function. So let's look at some intermediate steps first. So let's just set them up, some intermediate calculations. Intermediate steps first. So we need some results which we're going to bake into the final expressions. So let's set up these sets of derivatives which we are going to use a little bit later. Okay? So let's see if everybody is on the same page. So I'm going to need a dz. So these are just some quantities I need in setting up the final expression. So I'm going to have a wij with respect to layer L. And if you look back at the expressions, this is simply going to be ai of L minus 1. And you see that immediately because this is Cj of L is given by the sum of omega ij of L of ai of L minus 1. So if I pick out one of these terms, that is simply going to give me this quantity here. This means also that if I take the derivative of dz of j with respect to dai of L minus 1, so I'm just picking out one of the terms, then this is going to be wij, this unknown parameter here. So that's two intermediate steps, which we need when we are going to set up the final expression for the backpropagation algorithm. That's okay? Let's wait just a few moments so everybody gets the final result here. Okay. Next, we could now use a sigma z, which is given by the sigmoid function. So if we do that as an example, this is just an example. Next week, we are going to discuss different types of activation functions. So keep in mind that the activation functions can be considered like a parameter in your model. Then we know that this d of a of j for layer L with respect to dz j of L. This is something which we previously just called the derivative, but in this specific case, it's going to be the same when we have the sigmoid function multiplied with 1 minus sigma of Cj of L, like this. And this is nothing but Aj of L of 1 minus Aj of L, the output, like that. So let's now specialize to L equal the final layer. And then we are going to start calculating derivatives. So what we do now is simply then to set up the derivative of the parameters W and the bias B. So let's do that. And this is, again, the chain rule. But the chain rule applied to the cost function. So what we're going to do now is simply to calculate dc of dwjk in the output layer. And when I use the chain rule, what I get then is Aj, layer L, minus the target value, which I'm looking after, the one I want to reproduce. I have Aj, and this is multiplied with, so what I'm going to get now is this wjk of L, but this is a quantity which I need to break up again. So this quantity there is actually delta Aj of L of dc of j of L multiplied with dc j, final layer, So this is again the chain rule being applied. And if I use the sigmoid function, this is just going to be given by Aj. So if it is the sigmoid, it doesn't need to be the sigmoid. I'm just setting that one in because I get a simple expression. And then I have my AK of L minus 1. So what you have is the following. If you look at the expressions now, so let us single them out. So we have this term here, which comes from the cost function. This term, which is a derivative of the activation function. And then finally, we have the derivative here. So this term, which you see here, is actually given by these two terms. So let's single it out here. So let's just look at this one. This is cost function specific. So if I have the cross entropy for a binary case, that derivative will be different. The term which you have here, this one, so let's just ring this in here. This one is activation function specific. And you see now why it's so beneficial to use automatic differentiation, because if you change cost function, instead of you having to encode the derivatives, you can just use automatic differentiation to find the derivatives. So this is something which simplifies a lot, because this is the derivative of the cost function. This is the derivative of the activation function, the output layer. And this guy here follows simply from the expression which we had here, this term here, which we actually have in here. So what we are going to do now is to collect these terms and redefine this parameter delta J, which we had in the previous lecture. So what we are going to say now is the following. So we are going to define a delta J which is equal to the derivative of the activation function times the derivative of the cost function with respect to the output. And this function here was just Aj of L minus of Y of J, the target value. So that means that we now have an expression for dC dW of JK of L, which is given by this function delta J of L times, and then I have my AK from the previous layer, the output from the previous layer. Then it's also pretty straightforward to see that dC of d beta J, last layer, is simply given by delta J of L. So what we have now are the gradients for the output layer. And then we can set up gradient descent for the output. So that means that we could now simply call our gradient descent code because we have the expressions for the gradients. So what we would do then is simply to set up the following expression. So we would then have the gradients and we would then have a Wij for the last layer, which is updated with Wij from the previous iteration minus eta times this delta J of L multiplied with AI of L minus 1. And then I would have my Bj of L, which gets updated with the previous iteration minus eta times J of L. So let's do the final step. Yeah. Yeah.
For the presence of a cost function specific in an activation function.
Yeah.
Then you mentioned that is for that case it will reach either the activation function or the cost function. Yeah. It's important to have a general way to calculate the derivative of those functions. Yeah. Does that constitute a computational trade-off? Meaning, like, do we have to do like additional operations?
So if you use automatic differentiation, that normally gives you some. So this is a trade-off. It's an important trade-off. And if you can hard code the analytical expressions, that is normally the best thing. So in project number 2, we are going to ask you to play around with 3 types of activation functions. So in principle, we are going to leave this with automatic differentiation as an optional feature for you, because you would need to include the libraries, etc. So you can hard code them. Automatic differentiation requires some more floating point operations. However, your development time together with runtime, that is a project time. So if you use a month to develop the expressions for all the derivatives and hard code them, and then your program runs twice as fast, compared to you using automatic differentiation, where you only code the cost function and the activation function. If that takes 10 minutes against a month to do all the development, then your total time, project time plus runtime, is much, much smaller. So what is typically done in machine learning is that you often try different types of activation functions. And then clearly baking in the activation function and then using automatic differentiation saves you a lot of paper and pencil stuff. So there's always a trade-off. Automatic differentiation requires some more flops. But then if the development time is much, much longer because you have to calculate all the derivatives, then it's you who has to strike this balance.
Libraries used for this kind of application.
Automatic differentiation?
No, like analytical differentiation.
So the analytical differentiation, if you use symbolic Python or Mathematica, what it normally gives, it can translate everything into code, but it translates it in an inefficient way. And you have to sit down and simplify the code. Okay, I see that I'm running a little bit over time. So what we will do next week is to go to the general case, and then we will have the final. So we're going to put up this one, and then we're going to have the final expressions. But we're going to stop here today. So this is next week. And next week, we will also discuss the implementation of the back propagation algorithm. And then by the first lecture next week, you will have all the elements which are needed for writing your own code. And then in the second lecture, we will show you how you can write the code. But exercises this week and next week, they give you the basic steps for implementing your own code. Okay, let's stop here.